Hello, and welcome to this presentation on synthesizing private location data using real-world knowledge. This is work done by myself, Graham, and Hakan at the University of Warwick. We motivate our work by noting that existing methods for protecting the privacy of location data are crude and simplistic. This means that the resulting data typically has limited utility. Furthermore, existing methods are typically oblivious to the real world and fail to consider geographic features, which leads to nonsensical outputs. For example, people often be located in the sea or rivers. Finally, most researchers and analysts will typically want to use their own in-house data analytics tools with the published data, and only synthetic data in the same format as the input data provides this capability. This is because most existing work typically provides outputs for arbitrarily defined regions, which is of limited practical use. Ever since differential privacy has become the de facto privacy standard, it has been increasingly applied to spatial data. And although there have been many works on synthesizing or publishing DP-compliant trajectories, these works fail to publish data at the same spatial granularity as the input data. We find that it is non-trivial to achieve high utility by uniformly sampling feasible points. Finally, although there is some context-aware work, it lacks a meaningful privacy guarantee, which is a prerequisite for strong privatization. Hence, our work is unique in satisfying strict epsilon DP, generating data in the same format as the original data, contextualizing the synthetic data in the real world, and evaluating our methods with popular location analytics tasks. Before outlining our problem, let us briefly summarize differential privacy and some important properties. Its definition is shown here, and the core idea is that the result of a differentially private mechanism is approximately the same regardless of whether any one person is included. For example, if we took the mean height of everybody watching this video, the published result should be pretty similar if my height is included or not. The level of privacy is controlled by the parameter epsilon, with smaller epsilon values equating to higher privacy. Differential privacy has two important properties that we use throughout our work. The first, sequential composition, allows us to combine DP mechanisms to obtain a result that has a privacy leakage equal to the sum of the privacy budgets of the individual mechanisms. The second property, commonly known as the post-processing property, allows us to manipulate privatized data without affecting the privacy guarantee, so long as though we do not interact with the private data again. A common way to satisfy differential privacy is to use the Laplace mechanism, as outlined here. It is commonly used with numerical data and uses the Laplace distribution to add random noise to values. And so to our problem. Given a set of real points P, we want to generate a set of synthetic points S, such that we protect the existence and location of each individual in the dataset. We aim for the synthetic data to be as similar to the real data as possible, all while satisfying the requirements of differential privacy. One way in which we aim to enhance utility is by using publicly available geographic knowledge, which we will discuss soon. In any realistic setting, we may also want to consider the aims of an adversary and what knowledge they may have, and we specify this briefly here. Adversaries, however, cannot be successful, as differential privacy provides everyone with a degree of plausible deniability with regards to their inclusion in the dataset. Additionally, by synthesizing data, as opposed to merely publishing it, we weaken the relationship between the real and synthetic points further. So, what geographic information do we assume to be public knowledge? Well, we consider the road network, forests, and coastlines to be examples of publicly known geographic boundaries. We use the road network as a soft constraint for generating data, and other geographic features as a basis for creating out-of-bounds regions where we prohibit points from being generated. In our work, we introduced two data generation methods. The first uses existing differentially private methods for partitioning data, Once complete, we introduce a number of private methods for data generation within these partitions. Our second data generation method goes further by incorporating real-world geographic data, that is, the road network, as the basis for controlling the data generation process. And so on to our first method. We consider three partitioning methods: uniform grids, adaptive grids, and clustering. Other techniques for partitioning can be used as we design our method to be flexible and interchangeable. Once the data is partitioned, we consider three methods for generating synthetic data, which we find to be a non-trivial exercise. Again, other data generation techniques can be used if desired. With our uniform grid approach, we divide the region into a grid with dimensions determined using the guideline shown here. We then obtain the number of real points in each region. We then add random noise to the count in each region, as shown here. This completes the uniform grid approach. If the raw data is not uniformly distributed, then uniform grids are suboptimal. Hence, we also consider an adaptive grid approach. We again start with dividing the entire region into a uniform grid, using a slightly different guideline this time. As before, we add Laplace noise to the count in each region, and then we divide each region into its own set of regions, controlled by a uniform grid. We use a different guideline for the second partitioning, which uses the noisy count of the initial regions. The guideline is shown on screen. An illustration of a potential result is shown on the right. As a final step, we add Laplace noise to the number of real points in each of these final regions. Finally, we also use a differentially private clustering method to partition our space. We use the EUGKM method to find the centroids of clusters, which involves using part of our privacy budget, epsilon1. Having done so, we form Voronoi regions and obtain the number of points in each of these Voronoi regions. As a final step, we once again add Laplace noise to get the noisy count for each region. This completes the third and final partitioning approach. Having outlined our private partitioning methods, we now move on to outlining our three methods for generating synthetic data privately. Uniform sampling is as straightforward as you would expect. We continue sampling until we have n dash points for each region. Our weighted uniform approach divides each region into subregions. To decide the number of points to generate in each subregion, we use the noisy counts of neighboring regions and the areas of the subregions themselves. Having determined the number of points for each subregion using the guideline shown, we generate the points using the uniform sampling method. An example of the process is shown on the right of the screen. It is worth noting that both of these methods are private by default, as they do not interact with the real data at all. Our third data generation approach uses kernel density estimation, which is a powerful statistical tool that can be used as the basis for data generation through sampling. Its definition is shown here, with phi representing the all-important kernel function. Although there have been numerous attempts to privatize KDE before, none are suited to our setting, which requires us to sample multiple points from the kernel density estimate. Hence, we need to define a private kernel function. As its basis, we use the two-dimensional Laplace kernel, and, for convenience, we use it in its polar form, as outlined here. We define a separate kernel density estimate for each region based on the distribution of the real points within it. It is worth noting that other kernels can be used in KDE, but we find that they offer poor utility and/or are hard to privatize. The way in which we ensure the kernel is private is by setting the smoothing parameter for each region's kernel density estimate using the guideline shown here. We can show that this setting satisfies DP by considering the probability ratio of the kernel function at its two most distal points. With private KDEs defined for each region, we can proceed to generating synthetic data. To do so, we exploit an important yet convenient property of kernel density estimation. One can sample a random real point, sample a random value from the kernel function, and combine them to give a point that is equivalent to sampling from the KDE directly. We do this until we have n dash points in the region, whilst ensuring all points are within our predefined geographic bounds. As a final comment, we implement an even sampling approach in which a real point is sampled no more than lambda times. This balances privacy and utility by limiting the privacy leakage from possibly sampling a real point many times. Until now, our data generation methods have been somewhat blind to any underlying geographic structures. However, in most settings, location data is likely to adhere to the underlying structure of a road network. And as road networks are public knowledge, we argue that using them as a basis for data generation will improve the practical utility of the published data. We model our road network as a graph, with edges, which represent roads, and vertices, which represent intersections. Our process has 3 steps. We first add noise to the number of points along each edge using standard DP means. We then model the distribution of points along each edge with 2 sets of noisy histograms, one parallel to the edge and one perpendicular to the edge. Finally, we sample from these noisy histograms to generate the synthetic data. Step 1 sees us add Laplace noise to the number of real points along each edge. Although we could proceed as normal having done this, we find that this results in a lot of noise being added, especially to edges that have no real points near them. As such, we perform 2 post-processing steps, as illustrated here, in order to minimize the effect of the added noise. Importantly, as this is post-processing, the overall privacy is unaffected. In step 2, we form noisy histograms in 2 directions, as highlighted here. We find that the number of bins that is optimal is governed by the square root of the noisy number of points on each edge. As we are interacting with the real data, we need to add Laplace noise to the count of each bin to ensure the differential privacy is satisfied. The final step of the process is to generate synthetic data for each edge. We illustrate this process now. Consider this schematic in which the thick line represents an edge and the boxes represent histogram bins. To generate points, we first sample from the noisy histogram in one direction, and then the other. This leaves 2 possible locations, one on either side of the edge. And we toss a fair coin to decide which one to choose. The exact point is then generated based on the boundaries of the chosen histogram bin. We repeat the process until we have generated the correct number of points along every edge in the road network. Having outlined our methods, we now proceed to evaluate them using 3 real-world datasets, 2 taxi trajectory datasets, and a set of 311 calls from New York City. Geographic data is obtained from OpenStreetMap, and we find that the New York data is well aligned with the road network, whereas the data from Porto is less well aligned. For the trajectory data, we treat each point independently and associate them with independent individuals. Because we do this, each point has its own DP guarantee, meaning that there are no adverse privacy consequences from linking published synthetic points. To quantitatively analyze our methods, we use 2 utility measures. The first, normalized cell error, sees us divide our space into a number of regions. We then calculate the average difference between the number of real and synthetic points in each region. Whereas NCE assesses the overall distribution of the data, our second measure, mean edge distance difference, aims to quantify the synthetic data's alignment with the road network. The equation defining MEDD is shown on screen here. First, let's assess the data generation methods visually using data from Beijing. Although all approaches can broadly identify sparse and dense regions, the grid-based methods are evidently superior to the clustering-based method. However, The road network approach offers even greater visual similarity with the real data, as it can more easily capture the intricacies of the road network. Quantitatively, we see that using KDE is the best approach for generating synthetic data. As far as partitioning is concerned, grid-based approaches are better than cluster-based ones, although there is little difference between uniform and adaptive grids. When we consider the road network approach, we see that it is competitive and performs especially well in cities in which the data is well aligned with the road network. It also offers particularly low MEDD values, as one might expect. In terms of runtime, adaptive grid methods tend to be slower than uniform grid methods, but they offer better accuracy. The road network approach is consistently faster than the partitioning-based approaches, however. We also consider the effect the privacy budget has on the utility of the data. As expected, all methods exhibit an expected error profile. That is, error increases as the privacy budget decreases. The partitioning-based approaches all see runtime increase as epsilon decreases, as expected from the guidelines we introduced earlier. The runtime of road is immune to changes in epsilon, as the runtime largely depends on the number of edges, which is unchanged. The first location analytics tasks that we consider are range queries, in which we consider circular queries centered on 100 POIs. Range queries are important for businesses as they allow them to quickly assess how many customers are nearby, for example. We use the mean absolute error, as defined here, to quantify the error between the real and synthetic data. All methods outperform their baseline, which we model as the partitioning-based approaches with uniform data generation. Road is competitive for small radius queries, although it performs worse when the radius increases. We also consider hotspot queries, which have many key applications, such as advertising. We conduct the analysis by generating kernel density estimates across fine uniform grids. As with the range queries, all KDE approaches outperform the uniform generation techniques. Road performs very well, and it is particularly good for data that is well aligned with the road network. We also conduct some additional experiments. The first sees us match the data to the road network as a pre-processing step. In this case, the partitioning-based methods perform up to 18% worse. We also consider the case where the population density is less even. In these cases, road and uniform grid approaches are more robust than other methods. And finally, we conduct numerous facility location queries. All methods generate synthetic data that obtains nearly identical results compared to the real data. This emphasizes the real-world applicability of our work. In summary, we have shown that including public geographic knowledge is very effective at boosting utility for free. As far as our methods are concerned, our road network approach is effective in all situations, but especially when the raw data is well aligned with the road network. If it isn't, both grid-based methods are effective, with the final choice dependent on other characteristics. Clustering-based approaches are less effective, although they are good for very large datasets. Thank you for listening.